Hello everyone, welcome to another video. This one's for problems 39 through 43. I want to remind everyone the best way to learn from these problems is to try them yourself first and then check out these answers. So here we go. The end of the cutting cord on a gas-powered weed cutter is 0.15 meters in length. If the motor rotates at a rate of 2 rotations per second, then what is the tangential speed at the end of the cord? Okay, so the end of the cutting cord, a gas power wheel cutter. I think that's supposed to be the radius. Yeah. So the end of a cutting cord on a grass-powered weed cutter. So I'm thinking weed whacker, like this. And the length here, or the radius, is going to be 0.15 meters. That makes sense to me. Okay. If the motor rotates 20 times in 1 second, 20 times per second, well, that means the frequency is 20 hertz. Okay, and from that we can get the period is equal to 1 over 20. And so period is 1 over 20, which gives me 0.05 seconds. What are we looking for again? All right, tangential speed of the end of the cord. Okay, so we're looking for regular velocity of this point here. It's rotating around the circle. It's got a whole bunch of variables to it. It's got an angular speed. It's got a regular speed. It's got acceleration, centripetal, all that stuff. They want this regular velocity. How fast is it actually moving in meters per second? And to get that, we can use a very simple relationship. We just have to find the angular velocity, multiply it by the radius, which they gave us there. So how do we get this angular acceleration? Well, the angular acceleration is equal to 2 pi times the frequency. Or you could have it 2 pi divided by period. In both cases, that's going to give us the angular velocity. These equations are on your reference table, by the way. So 2 pi times my frequency, which was 20. Okay, so that means I have an angular velocity. I'm not going to, so angular velocity is equal to 125.66 rads per second. I'm going to check that with the other equation just to make sure. Actually, it would make very little sense why that doesn't work out because it's basically the same equation. Yes, I get the same thing using the period equation as well. So we get this velocity and we just multiply that by the radius and we will get our tangential velocity. So 125.66 multiplied by that 0.15 meters for the radius. That gives me 18.8, which is pretty freaking close to 19. All right, not bad. A 0.4 kilogram mass attached to the end of a 0.75 meter string is whirled around in a circular horizontal path. If the maximum tension of that string can withstand is 450 newtons, then what maximum speed can the mass have if the string is not to break? Okay, so we don't want to break the string. And it's attached, so we know the length of the string, 0.75 meters, okay? And it's whirled around in a circular horizontal path. If the maximum tension, okay, hold on, we got this weight here. That's going to cause problems, because that weight is probably going to add tension to this rope and potentially break it, which is, I believe, what we're trying to avoid. Okay, if the maximum tension the string can withstand is this, then what maximum speed can the mass have if the string is not to break? Well, you got to remember that that tension is what's causing the centripetal force that's keeping this thing rotating in a circle. So we don't want that. So because if we spin it too fast, the tension's going to get too strong. The centripetal force required to keep it moving in that circle would be too big. So centripetal force is equal to m times ac, ac being the centripetal acceleration, which the equation for that looks like velocity squared over radius. And so we get centripetal force is equal to mv squared over r. So to figure out what speed this thing can handle, we're going to solve this equation for velocity. So I multiply by r, so vc over multiplied by r. We'll divide it by m, and we'll find the square root. That should be equal to my velocity. So I plug in the numbers they gave me. It can handle a centripetal force of 450 newtons. It's got a radius, which they told us, 0.75 meters. Okay, and we divide that by the mass, which was 0.4 kilograms. And so that should give me the speed that I can rotate this thing around at. So 450 times 0.75, and then divided by 0.4. The square root second of that answer would give me 29. 29 meters per second. Is that an option? It is. D. Very nice. All right. The distance from the center of a Ferris wheel to a passenger seat is 12 meters. What centripetal acceleration does a passenger experience when the wheel's angular speed is 0.5 rads per second? So this one's a very simple application of what I call the bridge equation, the bridge between regular linear variables and angular variables. So velocity is equal to angular speed times r. So Ferris wheel, passenger seat is 12 meters from the center, so the radius is 12. What centripetal acceleration does the passenger experience when the angular speed is this? So we get an angular speed of 0.5 rads per second, and we end up with 6 meters per second is equal to the tangential speed. Now, why do I need the tangential speed when they asked for centripetal acceleration? Well, centripetal acceleration, again, the equation is v squared over r. So all I have to do is take this 6 squared and divide it by the radius, which was 12. And so that gives me 36 over 12, or just 3 meters per second squared for the centripetal acceleration. An object of mass 0.5 kilograms is transported to the surface of planet X, where the object's weight is measured to be 20 newtons. Interesting, 20 newtons, okay. The radius of the planet is 4 times 10 to the 6 meters. It's actually a small planet when you think about it. What free fall acceleration will the 0.5 kilogram object experience when transported to a distance this far from the surface of the planet? So you got to remember, if you want the weight of an object on a planet, you take mass and you multiply it by the acceleration due to gravity on that planet. Okay? So we can figure out what that acceleration is here, but they're not interested in that. We could plug in the mass, we can plug in the weight they gave us, we can figure out what it is here, but I don't know how helpful that would be. We'll probably do that in a second. But the problem is that they want us to find it in a different location, a distance of this from the surface of the planet. So basically, the radius of the planet plus this. So we're looking for the strength of G, the number value for G, at 4 plus 2 is 6, times 10 to the 6 meters from the center of planet X, excuse me. All right, so how do we do that? Well, there's actually an equation for G. The way you derive it is like this. If you set this force of gravity equal to the big gravity equation, G, m for the planet, little m for the object, over r squared, you can actually solve a general equation for this little g here by canceling out the m's. So G at any given location is equal to big G, which is a constant on the back side of your reference table, multiplied by the mass of our planet, divided by the radius squared. Now, this would make this problem really easy. We just plug this number in for the radius. We know G because it's on the reference table, but we don't know the mass of the planet. So to figure this out, we're going to have to figure out what G is at this radius, because they gave us the force of gravity. So let me explain what I mean. If you take the force of gravity equation, we'll go over here. So force of gravity equation is equal to m times g. The force of gravity was 20 newtons, like they said. And the mass of the object was half a kilogram, 0.5 kilograms. We can figure out that on the surface of the planet, 20 divided by 0.5 is 40 meters per second squared is the acceleration due to gravity at the planet's surface. So this is 4 times 10 to the 6 meters. So that's how strong G is here. Now they want to know another 2 times 10 to the 6 meters above that. So 6 times 10 to the 6 meters away from the planet. How strong is G here when it's 40 meters per second squared here? Now, we know what G is, and so we can use that and we can plug it in to the general gravity equation that I derived on the other page. So if we have this, we know what g is, 6.67 times 10 to the negative 11. That's on the back of your reference table, multiplied by mass of the planet, which is what we're currently solving for, divided by the radius that this number was given to us at, which was that 4 times 10 to the 6 meters number. Okay, and that should be equal to the 40 meters per second squared that we just calculated for g. So we can solve this for g. So I take 40, I'm going to multiply it by that 4 times 10 to the 6. So 40 times 4 times, no, hold on, 40, yeah, 40 times all of that. Okay, and then I divide that by 6.67 times 10 to the negative 11, and I should get the world's largest number. Yeah, so the mass of the planet is equal to 2.3988, probably rounded that, times 10 to the 18 kilograms. So lots of kilograms to make a planet. I am not surprised. So now that we have the mass of the planet, we could figure out what g is at that larger location, at that 6 times 10 to the 6 number. So we plug in big G is 6.67 times 10 to the negative 11, multiplied by the mass of the planet, which we just got, 2.4, like I'm going to round it now, times 10 to the 18 kilograms. And then we divide that by, oh, I forgot this was squared, I'm sorry. That's going to change things. So 6.67 times 10 to the negative 40 divided by 4 times 10 to the 6 squared, and then, no, it's multiplied. So 40 multiplied by 4 times 10 to the 6 squared, and then divided by 6.67, and then divided by 10 to the negative 11. I gotta redo this part. All right. Whew. Ignoring this, and ignoring this, and ignoring this. Okay, just solving for big M. Big M is going to be equal to 40 meters per second squared, multiplied by 4 times 10 to the 6 meters squared, divided by 6.67 times 10 to the negative 11. Okay, so rearranging this to solve for big M, it looks like that. So now that I've got it all in front of me the way it should be, I should be able to calculate this. All right, and then divided by 6.67 times 10 to the negative 11. All right, and my answer is 9.6 times 10 to the 24 kilograms. So it's even bigger than it was before. Okay, so that's the mass of the planet. And we're still not done. That's just fixing my mistake. So we've got this g m over r squared. So we have to solve for g. So again, big G is 6.67 times 10 to the negative 11. Big M is 9.6 times 10 to the 24 kilograms. We'll divide that by that 6 times 10 to the 6 meters squared number. And so 6.67 times 10 to the negative 11 times 9.6 times 10 to the 24 divided by 6, divided by 6 times 10 to the 6th all squared means that G at that level is going to be 17.8 meters per second squared. If you plug this all into your calculator correctly, that is our final answer. How does that go? 17.8 rounds really close to 18 meters per second squared. Not bad. Okay, lastly, an object orbiting the Earth at a height of 3 Earth radii from the center of the Earth has a weight of 1 Newton. What is the object's mass? let g at the surface be equal to 9.8 meters per second squared. Okay, so in order to figure out the object's mass, we're going to look at this equation. Fg equals mg, like that. And so we're solving for mass. So we take the weight of the object and divide it by g at its current location, which again is going to be 3 Earth radii away. So boom, 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 this far, at a height of 3 Earth radii from the center of the Earth. That is correct. Okay, so here it's 9.8. Let's figure out what happens if you doubled the radius. So if g is equal to this number, like we have done so many times now, and we doubled the radius, okay? So we plug into r, then that 2 is going to get squared, and we're going to have 1/4 our original value for g, okay? So whatever our original value of g was, which is 9.8, we would have 1/4 of it at that location. So 9.8 divided by 4 gives me 2.45 at that location. Now, let's, instead of doubling it, let's triple it, like the problem says, 3r. So that means g would be equal to 1/9, because you take 3r squared, gm over r squared. So we're going to have 1/9 the original value. So we take 9.8 divided by 9, and that's going to be 1.09 meters per second squared. Okay, so 1.09 meters per second squared is the acceleration at that location. So if it weighs 1 Newton at that location, we divide it by 1.09 meters per second squared, that should give us the weight of the object. So 1 divided by that number gives me 0.92 kilograms, which is again option C. All right, guys, see you in the next one.